Now after completing the chapter definite integral, I want to discuss with you what are the applications of integrals and definite integrals. So I am going to discuss with you the topic definite integrals, or you can say the area, because we use the definite integral and integral in calculating the area bounded regions by various curves, that is the area enclosed by a circle, by an ellipse, hyperbola and axis, parabola and latus rectum, etc., etc., and area of triangle by using the integration if its vertices are given. So I mean to say, I am going to discuss with you the applications of integrals. I am going to begin with very simple example, very useful example, and with the help of it you will be able to understand how to apply definite integral while we are calculating the areas of the bounded figures. Question is, find the area enclosed by the circle whose equation is x square plus y square is equals to a square. In class 11th, we have told you that if equation is x square plus y square is equals to a square, then it is an equation of circle whose center is at origin, that is 0, 0, and radius is of length a units. So ultimately, if I give the sketch, then what will come out? It will be the shape. This is x dash x, that is x axis, vertical one y axis, point of intersection of both is origin 0, 0. Radius of the circle is a, that's why the coordinates of the point A are a, 0, and the coordinates of the point B are 0, a. If one of the parts area is calculated and that is multiplied by 4, that will give us the area of entire circle. Here the radius is a, so we can say the area is pi a square, direct formula. But with the help of integration, to evaluate it, what we did, that we have divided one of the part out of 4 of the circle in like this. We have drawn, we have divided in the shapes of the rectangles of very minute thickness, so called dx, and height is along the y axis, that is what y. So this is a rectangle, small rectangle of height y and breadth dx. So area of rectangle is length into breadth, that is y into dx. Height is y and base, that is breadth, is very small dx. Such kind of rectangles will form from origin, that is from 0 to a, and if one of the area is obtained multiplied by 4, that will give us the area of complete circle. So area of circle is given by 4 times of 0 to a y dx. Y is the height, or you can say length, and dx is small width. So small rectangles made from 0 to a. So that's why I have written integration is basically a summation, 0 to a, sum of all those rectangles areas whose height is y and width is dx, y into dx. It's 4 times, reason being because there are 4 equal identical parts. We know that x square plus y square is a square. So in place of this y, what we can obtain the value of y from here? We have x square plus y square is a square, that's why answer of y is root of a square minus x square. So here in place of this y, if we replace root of a square minus x square, then this problem, that is the area, will come in the shape area of circle is equals to 4 times of y means root of a square minus x square, this into dx, 0 to a. Root of a square minus x square dx, direct formula is x by 2 root of a square minus x square plus a square by 2 sin inverse of x upon a. This is the result. which we have taken from the integrations, and it's 4 times as usual. Now limits are from 0 to a. First we will put the upper limit minus lower limit. So on putting first a in place of every x and then putting 0 and subtracting, we will get a by 2 into 0 plus a square by 2 sine inverse of 1 is 4 times. We know that sine inverse of 1 is pi by 2. So this become a square by 2 into 4 into pi by 2. Its net answer simplification will give us pi a square. So with the help of integration, we can calculate the area of bounded figures, and which comes under the topic of the application of integrals. As I explained you, we need to think that small strips either along y-axis or along x-axis needs to be made, and then we have to think for the width and its limit, and according to the requirement of question we will apply the problem or the formula of the integration, and we will get to know what is the area of that closed figure. Now I want to discuss with you another question based on the area of the closed figures on the topic application of integrals. This is the problem of the type where some curve, circle, parabola, ellipse, hyperbola or a line is given. Question is, find the area of region bounded by the curve. The curve is given y is equals to x square. So we can compare, it is the parabola of the type x square is equals to 4ay. We know that we have 4 types of parabolas. Y square is equals to 4ax, y square is equals to minus 4ax. X square is equals to 4ay and x square is equals to minus 4ay. According to the nature of the parabola given, we draw its sketch. So the question is, find the area of the region bounded by the curve. The curve is parabola of third category, x square is equals to 4ay, and the line y is equals to 4. Y is equals to 4 is the line and x square is equals to y. It is the parabola, or you can say it is a curve initially. We want to find the area of the portion between the line and the curve. So this is second type of problem based on the area of the closed regions. So first we will go to draw the rough sketch of y is equals to x square or x square is equals to y. Its parabola will take this shape upward. Because of x square, its wing will be in the positive and negative both sides of the x-axis. Now the question is, line y is equals to 4. It means that y will never change, x remain to change. This indicates the line y is equals to 4. Y is equals to 4 is this line. Suppose I am saying this is L and C is the curve. So this part I can indicate by drawing overlapping. This part's area we need to calculate bounded between the parabola and the line. To obtain the area, I have taken its half of the portion, because if I am able to obtain the area of the part O, P, Q, then I will make its double, and that will be the area of the part enclosed between line and the parabola. Now to find the area, small rectangles have been drawn from 0 to 4, because rectangles will start from 0 and go till 4, and its breadth is very small, say dy, and length is x. Area of rectangle is given by length into breadth. So the required area will be twice of the area of the part enclosed between 0 to 4 x dy. X is the length and y is small width, and such rectangles are forming from 0 to 4. So limits are 0 to 4 x into dy and its twice. Area is equals to 2 into 0 to 4 x dy. Now the question is, what is the value of x which can be obtained from the given equation of the curve? Y is equals to x square, so x is root of y. So 2 as it is into as it is, limits 0 to 4 in place of x root y, its integration dy. Integration of root y as definite will be y to power 3 by 2 upon what? 3 by 2. We have applied here the result, we have applied here the formula which is required, that is y to power n plus 1 upon n plus 1. After obtaining, calculating this entire, this become 2 into 2, 4 by 3, y to power 2 by 3, limit 0 to 4 is the 8, 8 4 ja 32, this is 32 upon 3 unit square is the area of that part which you can see as shaded in the curve, and that is 32 upon 3, the required area enclosed between the line y equals to 4 and the curve y equals to x square. Now I want to discuss a problem of the type where we will calculate the area of the part enclosed between two curves. Find the area of the region bounded by two parabolas. One is y equals to x square and second is y square equals to x. So first I can assure you, and you can see that both the parabolas having their vertex at origin. This is the first parabola, y equals to x square. This is the second parabola, x equals to y square. Point of intersection, first is at origin, vertex 0 0, and if these two curves will be solved by the two variable purpose, two variables method, we will get to know these two are intersecting at the point 1 comma 1. So x equals to 1 and y equals to 1 is the common solution of both of these curves. Now area of the required region is what? Fx minus gx. Now you will surprise what is fx and gx. The upper curves, this parabola is fx, and lower one, this is gx. So what we want to obtain? We want to obtain the area of the part enclosed between these two parabolas. That is, if I make the rectangle, suppose this, then its total height, suppose this, another height is this. So these two heights will be subtracted, fx minus gx. Fx means obtain the value of x from upper one, from this one, that is x equals to y square. So we can say it will be first thing root x minus x square, both are subtracted, and dx. Their integrations, root of x, its integration is 2 by 3, x to the power 2 by 3, 3 by 2, minus integration of x square, y equals to x square, it is x cube upon 3. Limits are 0 to 1, when limits are put, it is 2 by 3 minus 1 by 3 equals to 1 by 3. So ultimately, if two curves are there, we want to obtain the area enclosed between two curves. So first we will obtain the height from upper one, then from lower one, we will subtract like this, we will integrate it, and we will check the limits of such rectangles is from like in this example 0 to 1, it may change, it may vary, and this is obtained by solving these two equations of the curves. So, this way we can calculate the area of the region bounded between two curves. Now, one of the very important, very interesting, fascinating question based on area bounded regions I am going to discuss with you. Question is also very important on the point of examination view, that how to find the area of a triangle or a quadrilateral if the coordinates of the vertices are given in a plane. So, basic how to find the area of the triangle if coordinates are given, I want to discuss with you. Using integration, find the area of the region bounded by the triangle whose vertices are given by coordinates A 1, 0, B 2, 2 and C 3, 1. To find the area, first I want to tell you, you need to locate these points in actual location. 1, 0, say this point is A, B 2, 2, we can write it, this is A 2, 2 and C 3, 1. Approximately possible locations are given, and then from the vertex B a perpendicular is drawn and one is drawn from C. Now, to obtain the area of triangle ABC, that is of shaded part, we can say the required area of the triangle ABC is equals to area of triangle ABD. ABD, this area. Then plus area of trapezium, I am talking about this trapezium, BDEC, minus area of triangle AEC, this one. So, if this trapezium BDEC and the triangle these two are added, ABD, and the area of triangle AEC is subtracted, then we will get the area of required part, shaded region. Before we calculate area, we must know what are the equations of AB, BC and AC. To obtain the equation of AB, we will apply 2-point form. 1, 0 are the coordinates of the one end point and 2, 2 are the coordinates of the another end point. So, we here on the basis of the straight line 2-point form, y minus y1 is equals to y2 minus y1 upon x2 minus x1 times of x minus x1. That will be applied to obtain the equation of the side AB. Similarly for side BC, because here coordinates are 2, 2 and 3, 1. And similarly for AC 1, 0 and 3, 1. Okay. So, I can tell you in short that equations of the line AB, BC and AC by the 2-point form will be, equation of AB will be y equals to 2 times of x minus 1. Equation of BC will be y equals to 4 minus x. And the equation of AC will be y equals to half of x minus 1. 3 equations of 3 sides AB, BC and AC are obtained. So, the required area will be given by area of the triangle ABD. This is 1 to 2 twice of x minus 1 dx. Second area 2 to 3 4 minus x dx, and third area which needs to subtract is 1 to 3 x minus 1 upon 2 dx. Why? Because to obtain the first area of ABD, this we have obtained from 1 to 2. This is 1, this is 2, 1 to 2. Limits are from 1 to 2 and equation is x minus 1, it is twice the value y dx we are using. So, y is equals to 2 into x minus 1 is put here and dx. For the second 2 to 3, we are using the concept of 2 to 3 and this trapezium 4 minus x y dx. So, here y is 4 minus x, this is, and in the third in place of y it is half of x minus 1 dx. When we put these values integrates, we obtain it is twice of x square upon 2 minus x 1 to 2, 4x minus x square upon 2 2 to 3, and half of x square upon 2 minus x 1 to 3. When we put these limiting values and we calculate for the finally the simplified value will give us the area of the required triangle ABC is 4 by 3. So the area of the triangle, though it can be calculated very easily by using the concept half of x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. But if we are bound to calculate the area by using the integration, then these steps and this kind of method you require to follow to find the area by using the integration, as we have calculated here. For these particular data, area is 4 by 3 square units.